Hi, welcome back. Today we're going to be talking about product and quotient rules for computing derivatives. Okay, so let's go ahead and look at the function f of x is equal to 4x plus 7 over 5x minus 11. How do we take the derivative of this? Well, unfortunately, it's not as simple as taking the derivative of the numerator and dividing it by the derivative of the denominator. We need a special rule or definition to help us find the derivative. Now we could plug this into the definition of a derivative, and there's a proof. It's a little ugly. It's not much fun for non-math geeks, so I'm going to spare you that. I'm just going to get straight to the formula and show you how it works. Okay, so the quotient rule. If you have f divided by g, so you have the quotient of two functions, the derivative is given by the formula here. So it's the derivative of the first times the second minus the derivative of the second times the first all over the second squared. Okay, so let's go ahead and apply that to the case we have here. So again, the first function, that's going to be the whatever you have in your numerator, and then the second function, whatever we have in our denominator. Okay, so applying our rule, so it's the derivative of the first, so the derivative of 4x plus 7 times the second, so times 5x. Let me stop here and go back. Okay, let's try this again. So the derivative f prime of x is going to be equal to the derivative of the first, so the derivative of 4x, then times the second, so times whatever you have in the denominator, 5x minus 11, minus, now it's going to be the derivative of the second, so the derivative of 5x minus 11, times the first, so times 4x plus 7. And then this is going to be all over the denominator squared. Now if we are asked to, oops, that's a typo there. If we are asked to take the derivative but not simplify, you'd be finished right here. However, we are going to go ahead and simplify this one. So for simplifying, I need to distribute combined like terms in the numerator. The denominator, you're going to leave it as it is. It's factored. It's considered simplified. So in the numerator, I have 20x minus 44 minus 20x minus 35 all over our denominator squared. So combining my like terms, the 20x's cancel, and I'm left with a negative 79 all over 5x minus 11 squared. And that is the derivative of our original function, 4x plus 7 over 5x minus 11. Okay, here's another example. Again, I have a quotient. I have a numerator and denominator both with the variable x in them. So to take the derivative with respect to x, I need to use my quotient rule. So I'm going to take the derivative of the first, so the derivative of 5x squared, get 10x, times the second, so times x squared plus 1, minus, and now I take the derivative of the second, so the derivative of x squared plus 1 is, that's right, it's 2x, and then we're going to multiply this by whatever we have in the numerator, 5x squared. All of this over our denominator squared. Okay, and again for this one I am going to work through and simplify the numerators. So distributing my 10x, we get 10x to the third plus 10x. Distributing or multiplying the second term here, we get a negative 10x to the third. And this will be all over x squared plus 1 squared. Okay, now combining my like terms here, I have my 10x cubed cancel, and I'm left with 10x all over x squared plus 1 squared. There's my derivative. One thing I'd like to note is that the terms do not always cancel each other out. That's just something that happened in these two examples. Okay, moving on, now I want to look at a function. So now we have a function that looks to be the product of two smaller functions, both functions of x. Just like with the quotients, we weren't allowed to just take the derivative of each piece and multiply them together. That's not what the product rule says. The product rule says if you have the product of two functions and you wish to find the derivative of that product, you're going to take the derivative of the first times the second plus the derivative of the second times the first. Very similar to the quotient rule, but even a little bit easier. That's why I like to start with the quotient rule. The main difference here is we are adding them together, where in the quotient rule we were subtracting. And then of course we don't have the denominator. Okay, let's put this to use. Right here. So looking at our function f of x, again we're going to take the derivative of the first and then times the second. So the first is going to be x squared plus 5, and the second will be x squared minus 3x plus 9. So the derivative of the first, we have, f prime of x then is equal to, I want the derivative of the first, so the derivative of x squared plus 5 is 2x, times the second, so times x squared minus 3x plus 9. I'm not doing anything to the second, I'm just leaving it alone. Plus, now I want the derivative of the second. So now I take the derivative of x squared minus 3x plus 9, and we get 2x minus 3. And this is times the first, so times x squared plus 5. Now if we were instructed that you do not have to simplify, you would stop right here. I'm going to continue to simplify this one. Sometimes you will have a common factor that you can take out. Not in this case. I'm pretty much left with distributing, FOILing, combining my like terms. So let me go ahead and get started. We get 2x cubed minus 6x squared plus 18x. And now here I need to FOIL, so we get plus. I have 2x cubed plus 10x minus 3x squared minus 15. So combining my like terms, I have 2x cubed plus 2x cubed, so I have 4x cubed, minus 6x squared minus 3x squared for a negative 9x squared, or minus 9x squared. 18x plus 10x, so we have plus 28x. And last thing is I have a constant term of 15. So there is the derivative of this function right here. Okay, so here's another one. Do I have to use the product rule? Can I just go ahead and distribute e to the x? Well, you can distribute e to the x, you're still going to need the product rule. And if you distribute the e to the x first, you're going to have to use the product rule several times. So it's better to deal with it in its current form. Okay, so same thing, we're going to go through this. I need to take the derivative of the first, which is e to the x. And how do we find the derivative of e to the x? Or what is the derivative of e to the x? That's right, it's itself, it's e to the x. So I got derivative of the first times the second, x squared minus 3x plus 9, plus, now I need the derivative of the second, 2x minus 3, times the first, e to the x. If we're asked or told not to simplify, you can stop right there. If we are to simplify, again, a couple ways. You can distribute your e to the x. You can then combine like terms and see if anything will factor out. Kind of a sneakier way to do it is to factor out the e to the x, because I have e to the x times something, e to the x times something. So when I take out my e to the x, I'm left with x squared minus 3x plus 9 plus 2x minus 3. And now combining those like terms, I have x squared minus x plus 6. Usually if you're given a polynomial, you will factor this to see if it'll factor any further. I checked it and it will not break down anymore. So we are finished. Okay. Alright. Now it's time for you all to try some. Okay. Just a little reminder then. Product rule, quotient rule, you need to have these memorized. say them again and again and again and again in preparation for the test. I recommend that you write them down every time you use them until you have them committed to memory. Okay, so I've got a few more examples. Again, the best way for you to learn how to do mathematics is just to practice it. So on the next few examples, hit the pause button, try to work it out on your own. When you get stuck or when you're complete, go ahead, resume, and see how I work it out. Okay, so the first one here, S of t, clearly I have a quotient, and I'm going to be using my quotient rule. Notice that I have the variable in both the numerator and denominator. Okay, so using my quotient rule, I have the derivative of the first, so 800, times the second, so t plus 2, minus the derivative of the second, so the derivative of t plus 2 is just a 1, times the first, 800t, all over the denominator squared. And we're going to take this an extra step and simplify it. And like I said, often on the quiz, or you may have a pop quiz where I have you apply the rule but not simplify. Today we're simplifying. So I've got 800t plus 1600 minus 800t. Like I said nicely, everything's going to cancel out there. All over t plus 2 squared. So 800t's cancel, and I have 1600 divided by t plus 2 squared. Okay. How about the next one? What rule do we have to use here? Yep, we're using the product rule. This one I'm not going to simplify. So we're using our product rule. We have, this is going to be our first function, and this will be our second. Just a reminder, when e to the x, the derivative of e to the x is itself, e to the x. And how about the natural log of x? The derivative of the natural log of x is 1 over x. Okay, so we're going to use both of those rules inside the product rule. So y prime is equal to derivative of the first, so 0 plus 6 e to the x, times the second, we leave it alone, x plus the natural log of x, plus, now I'm going to take the derivative of the second, so the derivative of x plus the natural log of x. Derivative of x is 1, and the derivative of the natural log of x, as we just discussed, is 1 over x, and then times the second, or times the first, 36 plus 6e to the x. And this time the directions say, do not simplify. So I will leave my answer just like this. Those are my favorite. Okay. Next pair, very similar. So even before we start these, what's the difference between these two functions right here? Okay. And do we find the derivatives the same way? Well, the answer is yes and no. This first one here, we have 8x cubed e to the x. This is a product. We have to use the product rule. I have 8x cubed times e to the x. This is a function of x, and this is a function of x. But down here, in fact we did this one on our previous class, is 8's a constant. And so for this one here, I don't need to use the product rule. I could use the product rule, and when I simplify it I get the same answer, but it's much easier to just use the constant rule. Okay, let's take the derivatives. So this first one here, I have to use the product rule. Oh, actually, I write that down. Product rule. Alright, so here we go. I am taking the derivative of the first, and again remember, the first is going to be 8x cubed. So the derivative of the first, 24x squared, times the second, e to the x, plus the derivative of the second, okay, derivative of e to the x is itself, times the first, 8x cubed. If we didn't have to simplify, we'd stop right there, but I am going to simplify. I'm going a little bit further. If you're good at factoring, then you can take out everything at one time. I'm going to do it step by step. If I just take out the e to the x, then I have e to the x times 24x squared plus 8x cubed. Now maybe you can see that I am left with an 8 and an x squared that can be taken out of these parentheses. So factoring out the 8x squared in addition to the e to the x, so now taking out the 8 here, we get 3 plus x. And there's our derivative. And it's simplified. For the second example, like I said, this is a constant. So I'm just going to take f prime of x is just going to be equal to 8 times whatever the derivative of e to the x is, which is e to the x. Okay, so as you can tell, we solve them in a very different way. We use different rules, and the answers look very, very different. Okay. A couple more examples for us here. This first one, we're asked to take the derivative. This is average cost function. So if we're taking the derivative, we're looking at the marginal average cost. Two ways to approach this one. First, you can use your quotient rule. We do have a quotient. We have a function of x in the numerator and a function of x in the denominator. But what's another way of working it out? We could simplify term by term first, and that is often an easier way to do it. Okay, so I'm going to handle it. I'm going to go ahead and do it that way by simplifying first. So c of x is going to be equal to, I have 3x squared divided by x plus 5x over x and plus the 2,000 over x. So when I simplify them, my average cost function is 3x plus 5 plus 2,000 x to the negative 1. And now I will take the derivative. So I get 3. The derivative of 5 is 0, and then my last term here, I get negative 2,000 x to the negative 2. The reason I prefer to simplify it first algebraically and avoid using the quotient rule is because I'm going to have to plug a number in here, and this is a lot easier to work with than the other form. A lot easier to simplify. Even though they're equivalent, this is much easier to work with. Okay, what do you think about this second example? Same sort of thing going on. It is possible to use the product rule. We got a first and a second, or you could distribute and then take the derivative term by term. And again, this is going to be a case where it is much easier to distribute first. I don't care if you use the product rule, but sometimes you want to look for the easy way out. So we get 20, oops, sorry, this is not prime, multiplying it out. We've got 20 t to the 6th minus 32 t to the 4th plus 88 t cubed. And now I'm going to take the derivative like I would of any polynomial. Okay, so now looking to take the derivative, oops, g prime of t. Again, I'm using my constant multiple rule. I'm using my power rule. So I bring down my exponent and I get 120. Decrease it by 1, so 120 t to the 5th. 4 times 32, I get a negative 128 t to the 3rd. And then 88 times 3, I get 264 t squared. And there is the derivative of our product. Okay, time for an application. Wouldn't be calculus if we weren't doing applications. In the early 20th century, L.L. Thurstone found that a given person successfully accomplished n of x acts after x practice acts, as given by the following function. Find the rate of learning after 4 practice acts and after 40 practice acts. What do you notice? Okay. So, like all our other applications, we're going to take a minute to figure out what we're working with. And basically, we know that the number of acts that can be accomplished nx after x practice acts. Okay. So we have the number of acts, and then we have after how many times it's practiced. We are asked to find the rate. So if you want to find the rate of learning, you have to take the derivative of the learning function, which is n of x. And we want to know what it is with respect to x. So that's after how many practice acts. Okay, so first thing I need to do is take the derivative. How are we going to find the derivative of this function? Yep, good old quotient rule. So I have the derivative of the first times the second minus the derivative of the second times the first all over the denominator squared. This is one where it's really up to you if you're going to simplify it or not. I think it's worth simplifying. It's not very complicated. And remember, we have to evaluate this function now at 4 and at 40. So it's worth a little bit of effort. So distributing, I have 100x plus 3200 minus 100x minus 200. Same denominator. X plus 32 squared. Combining my like terms up in the numerator, you can see the 100x's cancel. 3200 minus 200, so I end up with 3000 over x plus 32 squared. Okay, so now I can evaluate my derivative at 4, and I've already worked this out on my calculator, so I've got 3000 all over 36 squared, and okay, evaluating this here on my calculator, I got 3.99, a bunch of stuff, so let's go with 4. Okay, so for what? Remember, this is a rate, so it's going to be n per x. So that means the rate of learning is going to be 4x per practice act. So after 4 practice acts, the person is learning at a rate of 4 acts per practice acts. Now what happens as we increase the amount of practice acts? So this time we're going to have 3000 divided by, I get 40 plus 32, so divided by 72 squared, which came out to be 0.997, so approximately 1. So it'll be 1 act per practice act. Okay, and there we go.